All right, welcome calculus students. This is the example I went over when people were on the field trip with Mr. Reynolds. So if you're in class that day and understand this example, then you don't have to worry about it. But if you weren't in class, I'm going to go through this example. This is a kind of a common example for related rates. So a 6 foot tall person is walking away from a lamppost at a rate of 4 feet per second. The lamppost is 24 feet tall, and how fast is the tip of the person's shadow moving? All right, so if we look at this problem, and we look at this lamppost, so the lamppost is putting out light, and one of those light beams goes across the person's head and creates a shadow in this area. Let's see, let's get a coordinate system going. So let's do y is up, and x is in the direction the person's moving. And in this particular case, the person is moving away from the lamppost. So their rate is constant, and they're moving at plus 4 feet per second. And what we want to do is we want to figure out how fast the tip of this shadow is moving. So I'll call the length from the pole to the tip of the shadow, I'll call this S. And so this would be ds dt. And this is what we're trying to find. We need one extra coordinate in here, and that's x. If you look up here, the dx dt, 4 feet per second, remember that's the rate that this x is changing with time. So every second this x grows 4 feet per second. And we want to figure out how fast the tip of the shadow is moving. So if we look at the geometry in this problem, we actually have two triangles. So I'll draw that out. So the height of this larger triangle is 24. That's the height of the lamppost. And the person is 6 feet tall. And then the base here, I've got x, and the whole thing is s. So if I break this into two similar triangles, I can use similar triangles in order to solve this. So I've got my big triangle and my little triangle. And so for the big triangle, this up and down leg is 24. For the little triangle, it's 6. And then for the big triangle, the base is s. Now if we go back over here and look at this drawing, we have to come up with another dimension for the smaller triangle. So I'm trying to find this dimension right here. And so if you look over here at this drawing, this whole length of the big triangle is s, and only this segment or section is x. So I need to figure out what this is. So if I look and see that the whole length is s, and this is x, then let's see here, the length, the length here is going to be s minus x. So over here for this little triangle, what I'm going to do is make this length s minus x. Okay, so I'm going to use similar triangles. And so the ratio of the big triangle, 24 over s, is equal to the ratio of the little triangle, which is 6 over s minus x. And so what I'm going to do is I'm going to cross multiply this. So let me see, let me add a page. Okay, so I'm going to rewrite that equation. So I've got 24, let's see here. Okay, so I've got 24 over s is equal to 6 over s minus x. And I'm going to cross multiply. So I get 24s minus 24x, I just distributed that 24, is equal to 6s. Okay, so now I'm going to combine like terms. So I'm going to subtract 6s from both sides. And I'm going to get 18s is equal to 24x. Okay, and so I'm going to divide both sides by 6, and I get 3s is equal to 4x. And since I'm going to what I'm looking to find is ds dt. I'm going to divide both sides by 3, so I'm just solving for s. So s is equal to 4/3 x. Alright, so now at this point, I'm going to differentiate both sides with respect to time in order to get my rates. And so if I do that, I get ds dt is equal to 4/3 times 1 dx dt. And then the last thing I need to do is just put in my rate for dx dt, which is 4/3 times 4 feet per second. And so the rate that the tip of the shadow is moving is ds dt. Okay, I got cut off. So ds dt is equal to 16/3 feet per second. Okay, so that's how you do one of the questions for the shadow problem. There's another thing that can be asked as well. So I'm going to go back. Oops, how do I do this? All right, I'm going to push pause. I'll be right back. Sorry. All right, I am back, and I figured this out. Okay, so let's go back to the original problem, because there's something else that you could be asked. All right, so I'm going to go ahead and erase a lot of this. Let me get actually, let me pause, and I'll be right back. Sorry. All right, sorry, back. All right, so we're going to look at another thing that can be asked in this problem. So let's reread the problem real quick. Okay, so a 6-foot-tall person is walking away from a lamppost at a rate of 4 feet per second. The lamppost is 24 feet tall. What we found before is how fast is the tip of the person's shadow moving. So this time we want to find something else. So I'm going to erase this last statement. And instead of looking at how fast the tip of the shadow is moving, what I want to do instead is I want to do another problem where I am looking at how fast is the length of the person's shadow changing. Okay, so what we're going to do is I'm going to go ahead and redraw out this problem. And I've got the lamppost, and I've got the person. And again, the lamppost is 24 feet tall, and the person is 6 feet tall. And the person's moving away from the lamppost at a rate of dx dt is equal to plus 4 feet per second. Now, if the person were moving towards the lamppost instead of a plus 4, that's not a good plus. Instead of a plus 4, if the person were walking towards the lamppost, it would be a minus 4. And the reason for that is I'm going to set my coordinate system the same way as I did before, where I've got y up and x is over. Okay, so let's actually draw the light and the shadow and see what's going on here. So I've got beams of light coming out of the lamp, and one of the beams of light I can trace across the person's head, and here's the shadow. So what I want to do is I want to figure out how fast the length of the shadow is changing. So I want to find dl dt. And again, like last time, what we're going to do is from the x coordinate to the person, I'm calling that x. And I have to call it x because the rate that the person's walking away is plus 4 feet per second, which means that this x is changing plus 4 feet every second. All right, so I'm going to draw similar triangles again. And I've got 24, and I've got 6. And this length I'm calling x, and then the length of the shadow I'm calling L. So if I break this into two similar triangles, a big one and a small one, this is 24 and this is 6. And the length of the small, or the base of the small triangle, if you look over here, is L, the length of the shadow. But for the big triangle is this whole thing. So with my defined lengths, this length is actually x plus L. So the base of the large triangle is x plus what I'm calling L, the length of the shadow. So if I use similar triangles, I'll do this over here on the left-hand side, then I've got 24 over x plus L is equal to 6 over L. And again, I'm going to cross multiply. And so I get 24L, and I'm going to distribute the 6 on the x plus L. So I've got 6x plus 6L. And let's see, I'm going to subtract L from 6L from both sides. So I get 18L is equal to 6x. Or I get L is equal to 1/3 x. And then the last thing I need to do here is just differentiate with respect to time. So I got dl dt, the length, the rate of change of the length of the shadow, is equal to 1/3 dx dt. And if I put in my dx dt is plus 4, so this is going to be plus 4/3 feet per second. And that's how fast the length of the shadow is changing. And that's how you do the shadow problems. All right, we'll have one more example, and I will send it out. All right, have a good one.